Alright, in this video we're going to be looking at the P-channel MOSFET as opposed to just the N-channel MOSFET. And I find the best way to describe this is using what's known as the CMOS inverter. Now in reality, the P-channel and the N-channel MOSFETs work in very similar ways. They're actually not that dissimilar. The only really difference with them is around the voltages that you apply to them. So I'm going to have my P-channel FET up here, noting the direction of the arrow. This is an E MOSFET, and it's going to be connected to 5 volts. And I'm going to connect that with my N-channel MOSFET down below, which I'm going to then connect to ground. And I'm going to tie the gates together and the drains and source together. Alright, so this is 0 volts, that's 5 volts, this is the input voltage, and this is the output voltage. Now this is known as a CMOS inverter, and we're going to see why it's called an inverter. It's basically a NOT gate when we analyze this circuit. So let's say for scenario 1, Vi equals 5 volts. Alright, so voltage, make sure that you can see that that's a voltage rail. Voltage here is 5 volts. Now, P-channel MOSFET, still a normally off device, alright, that doesn't change, except it requires a negative voltage from gate to source to be able to switch, alright, to be able to switch on. So if I was to have 5 here and 5 here, VGS P-channel is equal to 0 volts, and therefore ID through that device is going to be equal to 0. Alright, so this is an open circuit. Whereas if we put our 5 volts here, also connected together, the VGS of our N-channel is equal to 5 volts. Let's say these have a threshold voltage of 2.5, so they're all going to be turning on. So therefore ID equals some value greater than 0. Let's assume it's a short circuit. Alright, so we get 5 volts here, this turns on, so this FET comes on, and therefore this point here, V0, gets pulled down to ground, and V0 equals 0 volts. Alright, so do we see this again? Apply 5 volts in, 5 volts at gate, source and drain, all labelled up there. Alright, noting this one's been flipped around, just because it's on the top there. Alright, 5 to minus 5, because VGS is across this point here. VGS is here. With 0 volts, it's a normally off device, it's going to be off. So this point here is an open circuit between 5 volts and the output, while this one is 5 volts and 0, so VGS here is 5 volts, and therefore we get this device on, short circuiting out that to ground, and we get 0 volts. Let's look at scenario 2. In this case, let's assume that Vi equals 0 volts. Alright, so 0 volts here. We'll start with our P-channel again, so we'll put 0 here. Voltage from gate to source, VGS is equal to VG minus VS, so we get 0 minus 5, which equals minus 5 volts. And therefore ID is greater than 0. Right, so this device is now on because it's got a negative voltage. This is on the P-channel device, so we get a short circuit. Whereas we get our 0 down here, VGS for the N-channel, 0 minus 0 for 0 volts, ID equals 0, and that's an open circuit. So if we have an open circuit from V up to 0 volts, and a short circuit to 5 volts, therefore V0 is going to be equal to the 5 volts at the top of this example. So can we now see how it's an inverter? 0 volts in, gives 5 volts out, 5 volts in gives 0 volts out. So it inverts. If it's a low signal, it goes high, and if it's high, it goes low. And we can do that by using a P-channel device and an N-channel device. In this case, they're both enhancement mode. But it's a nice way to see how the P-channel device works.